Hello, this is Chris Chu. I'm glad to be able to present our paper here entitled Assessment of Airwell Performance in Single-Storey Terraced Houses at the University of Malaysia Sabah Colloquium of Academics 2021. The current ventilation design of single-storey terraced houses in Malaysia for years has been studied as recently as 2019 to conclude that they are poorly ventilated for thermal comfort. Notably, there's a paper by Leng et al. In Sarawak and Tinker et al. In Malaysia. The airwell in buildings is specified in the Uniform Building Bylaw 1984 as a basic ventilation requirement for utility, mechanical room, and washroom stairways with stated sizes and dimensions. So, do existing typical single-storey houses in Malaysia suffer from adverse cold inflow? And how would adverse cold inflow be eliminated, and how much improvement in airwell performance would result? Here's a picture of a recently constructed single-storey house in Malaysia. You can see whether this is going to be a comfortable house or not without air conditioning. So what is adverse cold inflow that I've just mentioned? Because I believe, I hypothesize that this is what has been causing inefficiency in the ventilation of buildings, or it's a chimney effect. So adverse cold inflow or flow reversals in solar chimney has been studied by Carnell and Lay, among others. And we ourselves at University of Malaysia Sabah, together with my students, found that by eliminating cold inflow, the airflow rate of a natural convection air cool heat exchanger could be enhanced by 45 to 90%. So what is our approach here? So start with a CFD simulation on a typical terrace house and the airwell similar to that analyzed by Leng et al. So here's the model. The dimensions are very closely extracted from the paper. Okay, it's 4 meters by 3 meters wide by 3 meters high. And then you got a chimney sticking out 2.55. Okay, this is an extended airwell. The airwell is adjacent to the room, and then it's extended by the chimney. And it's got windows entering the airwell, and also window entering the building for air inlet. You can see the arrows, and air outlet. And there are 3 points inside. The 3 points in the mid-plane of the windows where we would monitor the velocities and temperature. Okay, there are 4 cases we're investigating. First one is the typical one, which is a story plus chimney. Second one is a story plus chimney. It's a typical one plus a wire mesh blocker. Third one is no chimney except an airwell, and then no wire mesh blocker. The last one is no chimney, but there's a wire mesh blocker there of the airwell adjacent to the room. Okay, simulation. The tool that we use was a computational fluid dynamics software called Phoenix, supplied by CHAM of the UK, to solve the Reynolds average Navier-Stokes conservation equation for fluid mechanics. and it's been validated for use of natural convection of the chimney. Okay, the mean airflow rate and velocity at the airwell inlet window are shown here as the results of the calculation of the simulation. For case 1, you can see the velocity is pretty high. It's the highest of all 4 cases, and progressively, and compared to case 2, is much higher. Why? Because case 2, we put a wire mesh on top of the chimney. So the chimneys is working well, and the wire mesh blocker will really be it would really resist the flow and actually slow down the whole thing, which is what you would expect. However, case 3 is no chimney at all, right? No chimney and no blocker. You can see the velocity is much lower. It's 0.07. Now, case 4, if we add a blocker to it, the draft is improved. Well, 0.07 to 0.1, it sounds like almost 50% improvement. And you would expect the temperature to be much lower at the case 1, and then somewhat higher, case 2, and highest at case 3 because the airflow is lowest. But if case 4, where we put a wire mesh blocker without chimney, then the temperature has dropped by 2 degrees, which is significant. You can actually sense the comfort levels change. And all of them seem to be giving the kind of air changes satisfactory. Okay, case 1 is the values of the mean test room velocity was 0.51, which is close to the Lang et al.'s measurement at 3 points. The average velocity was 0.45, ours was 0.51. And then the air shaft mean velocity at the airwell top exit at the chimney top. Yes, the average was 0.4. The average was 0.53. Ours was 0.44. So the simulation, in a sense, is validated because it's about the right kind of order of magnitude within reasonable error margin with Lang et al.'s model. So the model setup is okay. So here are the temperatures comparing. This is without any chimney, case 3 and case 4. But case 3 has case 3 has no blocker. Case 4 has a blocker. You can see there's a slight improvement in the temperature, and you can see case 3 the velocities at the various points A, B, and C. There is some kind of instability there. At point number C, it seems to be lower, and then point B is going to shoot up high and then go down again. Whereas at case 4, A, B, and C are all pretty close to each other. So using wire mesh blocker does stabilize the flow and give reasonable thermal comfort. And the bonus feature is that with an cold air blocker as wire mesh, it actually acts as a physical barrier to intruders. For conclusions, a room in a single-story terraced house built with an adjacent airwell and chimney has been simulated for natural ventilation performance for 4 cases. And case 1, which is typical, appears to perform well in terms of ACH, but it requires additional construction, maintenance costs of a 2.55 meter high chimney. And the use of wire mesh blocker in cases 2 and 4 show that it enhances and stabilizes the ventilation by blocking the adverse cold flow at the airwell top exit. So that even without a protruded chimney, the airwell can provide stable airflow velocity at human activity level for thermal comfort in the current design of single-story terrace houses. If a chimney, like 2.5 chimney, is installed, you put a wire mesh blocker, it's not necessary. Okay. The wire mesh blocker can also act as a security against intruders. Okay, finally, we would like to acknowledge and thank University of Malaysia Sabah Research and Innovation Center for providing a grant with number SGA0034. And we would like to invite any question.